Picture this. You're looking at a massive, modern logistics warehouse. Or maybe it's a high-stakes search and rescue operation with literally hundreds of autonomous robots zipping all over the place. The central, totally chaotic problem we're dealing with is this. How on earth do you stop a swarm of robots from crashing into each other or into the walls, while still getting them exactly where they need to go as fast as possible? Because if even one robot fails or just stops for a second to calculate a route, the whole system can completely grind to a halt. And you know, the solution to this incredibly complex multi-robot navigation problem isn't just about throwing more computing power at it. It actually requires us to look out our windows, at nature, and then apply some seriously elegant geometry.
Welcome to today's Explainer. Today, we are going to demystify some truly fascinating research coming out of institutions like Coventry University and the Technical University of IASI. We're going to explore exactly how roboticists are combining the biological behaviors of the natural world, specifically swarm intelligence, with advanced mathematical smoothing techniques to perfect robotic movement. It is an absolutely brilliant fusion of nature and math, and it is completely reshaping how autonomous systems navigate our world.
Okay, let's dive into this. Here is our roadmap for today. 1. The path planning problem. 2. Inspired by the swarm. 3. Smoothing with Bezier curves. 4. Designing safe polytopes. And 5. Putting it to the test.
Starting off with Section 1, the path planning problem, navigating the chaos. So before we can really appreciate the solution, we need to understand the foundational challenge here, right? Getting one or many robots safely from point A to point B in environments that are constantly changing. Now, historically in the robotics field, developers were kind of stuck choosing between two main approaches, and both have some pretty significant trade-offs. On one hand, you've got global path planning. This is centralized. Think of it like a master controller overseeing all the robots. It needs to know absolutely everything about the environment beforehand, which is great for static, unchanging rooms, but it severely struggles with scale. I mean, as you add more robots, the computing power required just skyrockets, and it completely fails if the environment is unpredictable. On the flip side, you have local path planning. This one is decentralized. Every single robot figures out its own path based on its immediate surroundings, kind of chatting with nearby robots to avoid collisions. It's highly scalable and flexible for sure, but making sure all these independent little agents actually reach their final goals without getting stuck, that requires some incredibly complex algorithms.
And when we look a bit closer at traditional local planning methods, well, they have some pretty serious real-world flaws. For instance, classical methods like artificial potential fields use these virtual attractive and repulsive forces, but robots often get trapped in what's called local minima. Essentially, they get stuck in the corner and just assume it's the best spot. Then you have sampling methods like probabilistic roadmaps, which explore randomly, but they scale terribly when things start moving around. But actually, the worst part? Many of these older algorithms spit out piecewise linear, or PWL paths. This means the robot moves in rigid, straight lines. It stops, turns sharply, and moves again. These jagged, jerky movements are just terrible for the robot. They burn through precious battery life, cause severe mechanical stress, and literally lead to wheel slippage.
Moving right along to Section 2, Inspired by the Swarm, Nature's Algorithm. To fix these limitations with the classical algorithms, researchers realized something pretty amazing. Nature had already solved this problem. Nature already knows how to coordinate massive numbers of independent agents without a central controller, and this led them to something called particle swarm optimization, or PSO. PSO is a bio-inspired metaheuristic algorithm. I know metaheuristic sounds like a mouthful, but it's basically just a higher-level problem-solving framework. It directly mirrors the social behavior you've probably seen in your own backyard or on a nature dock, like the flocking of birds or the schooling of fish. In these natural groups, there is no boss bird up front dictating where everyone else should fly. Instead, they figure out the best routes entirely collaboratively.
So how exactly does this translate to multi-robot path planning? Well, the algorithm works in this really fascinating sequence. First, it initializes a swarm of possible solutions. You can picture these as robotic particles moving through the problem space. Second, it evaluates the trajectory of every single particle, checking things like path length, safety, and energy efficiency. Third, and this is absolutely key, the algorithm adjusts the paths based on the individual learning of each robot. And finally, step 4, it refines the path based on the entire swarm's shared social knowledge. Through this really cool blend of individual learning and social information sharing, the swarm collectively hones in on an optimal, completely collision-free trajectory.
Section 3. Smoothing with Bezier curves. Elegant robotics.
Okay, so finding the optimal general path is really only half the battle, because even with swarm intelligence, the raw paths it generates can sometimes still be pretty jagged if they're left unpolished. We absolutely have to fix those jerky, rigid movements that end up damaging the hardware, and this is where we see a huge contrast between two geometric approaches. Remember those traditional piecewise linear paths we talked about? They're exactly what you picture when you think of an old-school clunky robot. Jagged, stop and go, totally inefficient. The modern upgrade is swapping those out for piecewise Bezier curves. Bezier curves, specifically the quadratic ones used in this research, are polynomial curves that create paths that are smooth, naturally elegant, and most importantly, continuous. A robot following a Bezier curve never ever has to come to a jarring halt just to change its direction.
Now what's really interesting about this slide is how that blue line behaves. That is our smooth robotic path, formulated using those piecewise Bezier curves. You can see just how gracefully it sweeps around the sharp angular corners of those red obstacles. Now look at those purple dots. Those are the Bezier control points. Think of these points like invisible magnets, right? The path doesn't necessarily physically touch all of them, but they dictate the curve's geometry. They pull the robot's trajectory safely away from the tight corners without requiring it to stop and pivot. It is beautifully seamless.
Which brings us to Section 4, Designing Safe Polytopes, creating our safety margins.
But there's a catch, isn't there? Smooth, graceful paths are totally useless if they sweep too wide and cause the robot to crash into a wall. So to fix this, researchers use a concept called the safe polytope. If you check out the original free space in the environment, the large polygons you can see here, researchers explicitly ensure obstacle avoidance by shrinking that boundary inward by a very specific safety margin. This creates a strict subset called a safe polytope, which you can see highlighted by those dotted lines and colored inner regions. And this brilliantly illustrates how safe polytopes act as a virtual buffer zone. The algorithm is constrained so that it can only plan the robot's path within this inner safe area, keeping the entire thing well away from any physical threats.
The real reason this works so flawlessly comes down to a crucial mathematical property of Bezier curves. As the source text states, the entire Bezier curve segment lies within the convex hull formed by its control points. Now, a convex hull is basically what you'd get if you took a rubber band and stretched it around the outside of all those purple control points we saw earlier. What this means for our robots is incredibly powerful. Think about it. If the algorithm ensures that the metaphorical rubber band stays completely inside our safe polytope, it mathematically guarantees that the robot's smooth, sweeping curve is 100% guaranteed to stay safe too. There is literally zero chance of a collision.
And finally, Section 5, putting it to the test. Let's look at the simulation results.
So we have swarm intelligence to find the route collaboratively, and Bezier curves confined by safe polytopes to make it smooth and secure. Let's look at the undeniable data-driven proof that this combined approach actually works in practice. Researchers stress-tested this algorithm across a few different simulated environments. First, you have a sparse environment. It's relatively open, with isolated obstacles. The dashed lines show the paths generated by both linear and Bezier methods, successfully dodging the black obstacles. But the real test is that second scenario, the narrow passage. This is a highly complex, highly constrained environment where precise maneuvering is absolutely critical. This is exactly where the old, jagged linear methods usually fail and cause robots to scrape into walls.
So the crucial point is right here. When you contrast the data from that narrow passage test, when comparing the traditional piecewise linear paths against the new piecewise Bezier paths, we see a really fascinating trade-off. The Bezier path execution time is a tiny bit longer, 21.61 seconds compared to 19.92 seconds. But look closely at the maximum trajectory deviation. The linear path drifted by 0.232 meters off its planned route. The Bezier path, only 0.073 meters.
I really want to emphasize that number, 0.073 meters. That incredibly low maximum trajectory deviation proves that while the swarm and Bezier approach might take just a fraction of a second longer to compute, its navigational precision is vastly superior. In a tightly packed warehouse, or say, a delicate surgical environment, that tiny difference in deviation, that's the difference between a successful operation and a catastrophic crash. It dramatically enhances practical reliability, and it extends the life of the robotic hardware by minimizing all that mechanical stress. So what does this all mean? By combining the social problem-solving skills of a flock of birds with the geometric elegance of Bezier curves, researchers have unlocked a completely new level of safe, smooth, and scalable robotic navigation. And it leaves us with a pretty provocative thought.
If we can perfectly coordinate a massive swarm of autonomous machines using the logic of birds and some clever algebra, where else in your everyday life might swarm intelligence revolutionize how things move? From traffic grids to global delivery networks, the biological algorithms of tomorrow are already here. Thank you so much for joining me for this explainer, and I really hope this sparked your curiosity.